If you zoom in far enough, past the molecules and into the subatomic void, you find out quickly that the universe hates perfection. Deep space is loud. Dead stars are constantly throwing off cosmic rays, bombarding everything in their path, and actively disrupting the microscopic fabric of reality. Your device survives this constant radiation barrage because standard computer bits are stubborn. A standard 1 or 0 is a rigid, isolated switch. It takes a massive amount of energy to accidentally flip it. But quantum computers don't use standard bits. They use quantum bits, or qubits, which exist in a delicate, fluid state called superposition. Mathematically, a qubit can be a 1, a 0, or a complex combination of both at the exact same time. This equation is where a quantum computer draws its immense processing power. So, the scale of the engineering challenge is staggering. We are trying to build the most capable machine in human history out of a mathematical state that, frankly, refuses to stay intact. The very fluidity that gives a qubit its power also makes it uniquely vulnerable. It is hypersensitive to the physical world around it. If the universe interacts with it in any way, even with a single microscopic burst of thermal heat from the room, it acts as an observer. This triggers a process known as decoherence. The moment that observation happens, the delicate quantum state collapses. The qubit violently snaps out of superposition, picks a boring 1 or 0, and destroys your entire calculation. It is like trying to build a 100-story skyscraper out of wet sand. You might stack it perfectly, but the slightest passing breeze will cause the whole thing to come crashing down. This leaves physicists with an impossible paradox. You cannot engineer an error-free supercomputer out of subatomic parts that shatter the moment they touch reality. Eventually, scientists had to face a hard thermodynamic reality. Fighting the universe at a subatomic level is a losing battle. Creating a perfectly isolated, error-free qubit is a mathematical dead end. What we can actually build in the lab is called a physical qubit. These hardware components are messy, they are inherently glitchy, and they are practically guaranteed to fail. But instead of trying to force these individual pieces to be flawless, engineers pivoted. They decided to overwhelm the flaws using massive macroscopic redundancy. They abandoned isolating a single fragile bit and instead began entangling hundreds of glitchy components together into a tightly knit network. To fix the unpreventable errors of the quantum world, the strategy shifted from solitary perfection to interconnected volume. This brings us to the logical qubit. It is not a physical object you can touch. It is a simulated, invincible state of data generated entirely by the combined effort of that massive team of physical qubits. Think of them like a highly trained choir. If one individual physical qubit gets hit by cosmic noise and generates an error, it drops out of tune, threatening the entire performance. But through an algorithm known as quantum error correction, the surrounding qubits instantly recognize the mathematical anomaly. The rest of the choir is singing the right note so loudly that they forcibly overwrite the failing qubit, instantly snapping it back into perfect alignment. The machine doesn't magically stop errors from happening. It is explicitly designed to outsing its own mistakes with such volume that the final calculation remains completely untouched. But there is a massive engineering catch. Maintaining this flawless mathematical illusion requires an enormous physical tax. As this visualization shows, the required redundancy is staggering. It takes roughly 1,000 messy, error-prone physical components to sustain just one perfect logical qubit. To run simulations that could actually discover life-saving drugs or break standard encryption, we need a machine operating with hundreds of these perfect logical units. Multiply that out. That means building an array of hundreds of thousands of individual, imperfect physical bits, all pulsing and correcting each other in perfect unison. And shielding that massive network requires an extreme footprint. You need towering dilution refrigerators, packed with incredibly dense tiers of twisting microwave lines, just to keep the system cold enough to operate. It forces us to take these delicate, fragile subatomic equations and physically manifest them as towering, freezing, macroscopic monoliths. The most precise, advanced technology we have ever conceived doesn't exist because we engineered out every flaw. It exists because we accepted those flaws and built a system smart enough to fix them in real time. Perfection is just well-managed imperfection. To see exactly how these beautifully imperfect machines are going to shape our understanding of life itself, check out our next video on the future of quantum biology. Keep asking questions, and we'll see you there.
Thanks for watching. Please like and subscribe to Logic Lab 77. And stay safe.